section, we described the Internet as a network of networks bound together by a common IP protocol, an Internet protocol. In this section, we're going to discuss protocols, the IP protocol in particular, and examine how it works across multiple network systems. Protocols are essentially contracts between what I'll call East-West systems. They are loosely based on the OSI model. The principles of the OSI model are very important, that is, of segregation of responsibility among various layers and contract peering, that is having a contract between peer implementations of a protocol. The exact layers of the OSI model don't necessarily map well into the Internet protocols or other protocols, but they do give us a framework and a template, and that template is well used in many systems, including the Internet. In the diagram we have in front of us, I've shown a desktop PC, which would be in your home typically, or in a business, and I've shown 3 layers of a protocol. There are actually 4 here. The first is the Internet protocol itself, which is the primary subject for today, and it is supported by 2 different link layers. So the IP protocol in this diagram can be considered a layer 3 or a network layer, and the 2 underlying protocols, Ethernet and Wi-Fi, another IEEE protocol, would be layers 2 and 1, so that would be a link layer. And then the actual physical cable between the 2 systems, between the desktop PC and the home router, would be layer 0, the physical layer. And protocols really have a contract. The only contracts that are bound here is a contract between the IP layers, a separate and different contract between the Ethernet layers. The Category 5 cable is a physical layer. So apart from specifying the characteristics of that cable, there's no other contract at the physical layer. The protocols have strict rules and standards around the format of messaging, procedures, and data that is exchanged at the IP layer between the peers, but there's no physical connection between these peers. It's a logical connection, and it is really honored through the layers that support it. The practical implementations of protocols also involve interfaces, north and southbound interfaces. So these are the southbound interfaces between the IP layer and the link layer. The specification of the protocol itself is in an IETF, an Internet Engineering Task Force request for comment, RFC, that has been adopted, and specifies how the messages will be passed, the exact formats, and how they are to be packed and unpacked. The interfaces north and south are not specifically covered in the protocol. They are left for implementation by the system developers. So the company and engineers designing the desktop PC, and actually the ones designing the chipsets that are used in the PC, are responsible for building an internal interface between Ethernet, for example, and IP. Those interfaces are not exposed, and so they can be different for different suppliers and different implementations. The way the protocols work is if you are using an application on your desktop PC and that application wants to send a message into the Internet, what would happen is the application has an interface to the IP layer and would pass the data to the IP layer for transfer. The IP layer will be responsible for segmenting that information and breaking it into IP PDUs, protocol data units. Those data units are then passed to the Ethernet layer, and the protocol data units that are built by the IP layer are going to be somewhat different than the Ethernet frames. So a frame at the Ethernet layer is the logical equivalent of a protocol data unit at the IP layer. Once that information is passed to the Ethernet layer and it's broken into frames, then Ethernet will transmit it over the cable. The peer Ethernet implementation will receive that information and then pass it back up to the IP layer. In a home router, then that we're going to see a little later how that information goes out into the network. So once again, there's no physical connection between the IP layers and their peers. All the information has to pass over a physical connection. In this case, I've chosen Cat5. Now let's extend our example a bit. We'll add a couple of more network elements to the diagram and trace that through the entire path to understand how the IP protocol layers interact with each other and how the link layers transmit the information. So again, the important point is that the contracts and the communication is on a peer basis, IP to IP. In the extended example, I've taken some liberty and I've combined what are really two network elements, and that is a DSL multiplexer and a router called the BRAS, Broadband Remote Access Server. And those are really two different elements. The DSL multiplexer really terminates the DSL line, has DSL modems in it, and DSL technology that are compatible with the home router, and it typically communicates on a layer 2 basis, either ATM or Ethernet, with the BRAS, but I've combined them two just for simplicity in our diagram. I think the combination really illustrates the different link layers that can be used in an IP network. So we traced the packet from our application in our desktop, web browsing experience, for example, and we noted how it went through the Ethernet layer, back up to the Ethernet layer and the IP layer in the home router. From there, I said it went out on the internet. A couple points worth making here are the IP layer, when the packets are constructed, that is the PDUs, the IP PDUs or IP datagrams they're sometimes called, they're done in a way to really prevent breakage at the Ethernet layer. That is, the transmit size of the frames at Ethernet are known by the IP layer because that's an existing local interface. And so the IP layer will hand to the link layer frame packets that become what are called service data units inside the Ethernet frame that will fit within the frame boundaries of the Ethernet. Those frames are then forwarded over the physical cables we described before, and now the PDUs that arrive at the IP layer will be sent over a DSL line. The DSL line uses a completely different technology, of course, as we stated earlier, but that information is going to travel over the phone line and at the IP layer in the BRAS. So the DSL multiplexer will terminate the DSL technology and send it to the BRAS via either ATM or via Ethernet. In a typical BRAS, then you're going to have an optical connection, an Ethernet optical connection that will travel to the web server, and that is simplified here, but it would be via an entire routing network, and there would be multiple routers typically involved. So we have a packet that's traveled over an IP network and is traveled over three different physical layer and link layer technologies: Ethernet, DSL, and Ethernet over fiber. That is really the one of the real strengths of the IP protocol. The IP protocol contracts between all the IP layers have been met. Another point worth making is that it is at the IP layer where is the only layer which true switching takes place. The link layers, like the Ethernet layers, are point-to-point. The DSL phone lines terminate on a particular multiplexer, and there's no opportunity to switch that to another multiplexer. That's not true at the IP layer. The IP layers, we'll see later, has routing choices, and those routing choices are dynamic and can change. That means that successive IP packets could travel different paths, but depending on the state of the network when they are launched. So we'll get to see a bit more about that later. If we add TCP and HTTP, we can start to see how the IP layer provides support to the TCP layer and the HTTP. The TCP layer is a transmission control protocol, and it provides end-to-end transmission that is error-free for the particular packet or data segment that's handled from upper layer protocols such as HTTP. It sends the packets via IP, and IP is a best effort protocol, so it will attempt to deliver the packets, but the IP layer has no acknowledgement as part of the protocol, nor error correction, nor does it even check the error inside the user data that's transmitted. It does check the header data to make sure the IP packet maintains its integrity as far as the header is concerned, but not as far as the data. TCP, on the other hand, ensures in-sequence delivery of information from layers like the HTTP layer, and will engage in retransmission. That is, it will require retransmission if the IP layer for some reason loses a packet or a packet is corrupted. And it does this through a series of acknowledgments, which we'll describe later. What are the pros and cons of protocol stacks? Well, there aren't too many cons other than really the fact that in some ways it may be a little more inefficient than it might be if one had a purpose-built set of software, but the pros far outweigh it. Abstraction and simplification. That is extremely valuable because we've abstracted the functions of TCP and IP and so forth. That means that we've made it simpler to develop. We can focus on what we need to focus on in IP and not make the packets too complicated, and we've really placed responsibility where it belongs at each layer. Encapsulation. I can replace an IP protocol stack or part of the protocol stack without touching other parts of the design. That means if I need to update or replace the TCP layer, I can do that. I can do the same with the IP layer. It also means that they're distinct from each other, and one part of a stack might work with different Ethernet implementations and different DSL implementations, provided I meet the north-south interface requirements. And then finally, portability. You can buy stacks that are software stacks that are written by companies, and you can port them to a wide range of operating systems and a wide range of processors, and you can have them interwork with each other. So for all of those reasons, protocol stack approach, the OSI model, and has really aided the internet, and without that idea, even though it's pretty much a template and not a strict model, we could not have the internet function in the scale it functions, nor with the reliability. The reliability in this instance is really added by TCP for reliable delivery, although the reliability of transport itself, we'll see later, is a function not only of IP, but also the underlying physical technologies, the optics, phone line, and all the network elements that go to contribute to the various transport technologies that we see here.